system of our periodic motion. This is the simplest system. It is composed by, this is a spring, and this is a object. This is a body, and this is a fractionally horizontal glide. And then the body, the screen is contact with the body. So the body can move along the glide. So if we build an axis and the horizontal direction as the x-axis and vertical as the y-axis, so we will then the body will move along the x-axis. Now we can neglect the mass of the spring. So we can say the mass of the spring is 0. And then the horizontal spring force acting on the body. So when the spring is stretched or compressed, then the spring will exert force on the body, and the force will be put to right hand and may be put to left hand. So when the spring is stretched, then the force will point to left hand. And if the spring is compressed, then the force is toward to right hand. So this is the simplest system. Can be in periodic motion. We try to describe the motion of this system. So firstly, we should build the coordinate system, and the origin point or the origin or. So if we build an axis, we must choose an origin point. Bro. So we choose a special point as the origin point. It is the equilibrium position. The equilibrium position means there is no force. There is no force acting on the body. So no force acting on the body means the spring is even real. The spring is not straight or not compressed.
You can follow me?
I will follow.
MJ.
We need just this one.
So we must,
Please.
to describe this system, we must choose the origin point, or it is the origin, the equilibrium position. The second one, the x value. The x value choose the equilibrium as the origin point. The x value, it is also the change in the length of the spring. So it is the change in length of the spring. This is the spring.
Yeah, cool.
And this is the body. So we choose the this point. It is the equilibrium position, and in this point, the spring is in free, no stretch or no compressed, and we chose this as the x-axis. So the x value, it is such as if the body is moved to this position, and the distance, it is the x. So the x value, it is the component of the displacement of the body from the equilibrium position. So this is x. And because when in equilibrium position, the spring is in frame. So the x value is also the change in length of the spring. Because when the body is in this position, then the spring will be straight to this length, and the distance is x, and so this is the change of the length of the spring. And the fx, it is the x component of the spring force acting on the body. So because the body just move along the x axis or along x direction. So all the value, it is the x component. So the fx, it is a force. The x component of the spring force acting on the body, because the force, this is the spring. The spring will exert the force on the body. Such as if the body is in this position, then the force will be in this direction. So this is fx, and the x, the x is the x component of the acceleration. The x component of the acceleration, because there is force exerted on the body. So according to Newton's second law, the force will cause acceleration. So the fx will result in ax. So will result in acceleration of the body. So the relationship between fx and x is this. This is the Newton's second law. So this is the coordinate system, and this is the quantities. Quantities we should use to describe the motion. We analyze how oscillation occurs in this system. So when the body is away from the equilibrium position, so if the body is moved to this position, then the spring will exert a force on the exert force on the body, and the direction of the force is toward left. It's in this direction. So then the force will pull the body back to the equilibrium position. So it means the direction of the force is different from the displacement. So if the body is moved to this position, then the spring is compressed. The spring is compressed, then the spring force acting on the body, it is in which direction? Yeah, it is to the right. So the force is to the right. The force is to the right, so it will push. It will push the body to the equilibrium position. So we can say the force is always in different direction to the displacement. It is always have the tendency to pull the body to the equilibrium position. So we say this kind of the force is restoring force. It is the restoring force because the force is always tended to push the body to the equilibrium position. So this is the process of the oscillation. So the first one, when the displacement x is larger than 0, is positive. The positive means if we trace the right as the positive direction. So the displacement is positive means the body is moved toward the right hand. So the body move to right hand, then the force exerted by the spring is to the left, and so it is the restoring force Fx is negative. The force is negative means the acceleration is negative. So the acceleration is pointing to the left hand, and finally therefore we are pulling the body back to the equilibrium position or back to x equal to 0. Now the body, the second one, the body is come back to the equilibrium position. When the body is back to the equilibrium position, then the displacement is 0. The displacement is 0, so the restoring force Fx is 0. So the acceleration is also 0. So the x is 0, so the glider has 0 acceleration. So at this point, there is no little force along the horizontal. Now the body at this position, the body has 0 acceleration, but the body will have a velocity. The body still has a velocity, so then the body will still move to the left hand. The body move to the left hand. This is because the inertia. Because the body at this point have a velocity point toward the left hand, so the body will still move to the left hand, and then the body will have a negative displacement. The body has a negative displacement. Then the restoring force Fx is positive. Fx is positive, so the force is pointing to the right hand. The force pointing to the right hand, so the force we are pushing the body back to the equilibrium position. So when the body back to the equilibrium position, then the body complete a cycle. So we can say the oscillation always occurs if the force is a restoring force that tends to return the system to equilibrium position. So if we want to judge the motion is or loss, the oscillation, we can say, firstly, we can judge the force is or loss or restoring force. If there is restoring force, then the oscillation will arise. Now, if we want to describe the oscillation, we want to describe the oscillation quantity. So we should use some new terms to describe the oscillation. The first one is the amplitude. The amplitude, it is the maximum magnitude of the displacement from the equilibrium position, and it is always positive. So the amplitude, it is the maximum value of the displacement. Such as like this, even the body can move to right hand, and the maximum value is x. So the displacement is x. So the amplitude. We use the air refer to the amplitude. The first letter. And the second one is the period. The period. It is the time for one cycle, and it's always positive. And the unit is second. So the unit of for the amplitude is the meter. And the third one is the frequency. The frequency is the number. It is the number of cycles in a unit of time, and it's always positive. The unit is hertz. The hertz we can write as the frequency. The unit of frequency is hertz, and we can write it as hertz. Hz. And it is the number of cycles in a unit of time. The unit of time, it is 1 second because the unit of time is second, so it is the number of cycles in 1 second. It is the frequency, and it is always positive. Now, the frequency, it is also the reciprocal of the period t. So the frequency, the period, and the frequency, they have a relationship. The one hertz, we can write it as 1 hertz, and it is one bicycle per second. It is the cycles per second. So the F is equal to 1 over the frequency is equal to 1 over the period. So this is the relationship between the F and the T. So if we already know the period, then we can find the frequency. The F is equal to 1 over T. And if we already know the frequency, and then we can find the period. The fourth one is the angular frequency. The angular frequency, it is the number of cycles in 2 time. So the difference between frequency and angular frequency, the frequency, it is the number of cycles in unit of time. So it is always the number of cycles in 1 second. And the angular frequency, it is the number of cycles in 2 pi time, or in 2 pi second. And the unit is radial per second, because and then we can find the relationship. We use omega refer to the angular frequency, and it is equal to 2 pi f, and the f is the frequency, and the f is equal to 1 over t, so it is equal to 1 over 2 pi over t. So there are 1, 2, 3, 5. There are 5 terms we will use to describe the oscillation. And then the relationship among these terms we must remember. The first one is this: the relationship between the frequency and the periodic. And the second one is the angular frequency. The angular frequency with omega to refer to it, and it's equal to 2 pi f, and equal to 2 pi over t. So if we already know, if we are given the t, the period, then we will find the f and the frequency, and the angular frequency and the frequency. And if we already know this, so we can find the two other terms. Now look at this problem. A medical imaging device produces Bluetooth sound by oscillating with a period of 0.4 microsecond. What is the frequency of this oscillation? And the second one, the frequency of middle C on a typical musician in instrumental is 264 Hz. What is the time for one complete oscillation? The first one we are given the period and ask us to find the frequency. So how can we find the frequency?
We use 1/t.
Yeah, well, F is equal.
Equal to 1/t.
Yes, F is equal to 1/t. But we should notice that this unit is microsecond, and the unit of period it is second. So firstly, we should transform the micro unit to the microsecond to second. One microsecond is equal to how much second?
16, 6, I don't know.
Yes,
10
6.
minus 6.
So the F is equal to 1/t, and the T is 1/0.4 10 power minus 6, and the unit is Hertz. So this is the first problem. And the second one, we are given the frequency and ask us to find the time for one complete oscillation. The time for one complete oscillation it is the periodic. So the time for one complete oscillation is just periodic. And so in this problem we are given the frequency. Also the T is equal to 1/f. Now, can you find for this problem? What is the angular for frequency of the musician in instrumental? So what is the angular for frequency? What is the angular for frequency of the middle cell? The angular frequency.
Angle.
Angular. Frequency.
Angular frequency.
Yes. How much is the angular frequency in this problem? So we are given the frequency. So the relationship between frequency and angular frequency is what? So there are period F frequency and the angular frequency omega. So the F is equal to 1/t, or the T is equal to
1/f.
1/f, and the angular frequency omega is equal to
2/f equal to
2 pi
f
2 pi f, and it's equal to 2 pi
over t.
t. Yes, 2 pi over t. So in this situation, we are given the frequency. So the angular the frequency is 264 Hz. So the omega is equal to 2 pi times 264, and the rate and the unit is radian per second. So this is the angular frequency.
Teacher, the relationship is these three formulas or that's just previous?
Yes.
Just period or these three formulas?
Sorry.
The relationship,
Yeah, this is the relationship between this.
these three formulas,
Mm.
all of this.
And all because look at this. A bottle and anchor bounce up and down with the waves. And the bottle will move 6 cm above and 6 cm below is equilibrium position and makes 1 complete up and down cycles every 5 seconds. What are the amplitude, period, frequency, and angular frequency of this motion? So we are asked us to find the 1, 2, 3, 4, the four tones, the 4 quantities, and we already know the ball moves 6 centimeters above and 6 centimeters below its equilibrium position, and makes 1 complete up and down cycles every 5 seconds. We know at the first one the amplitude. So the amplitude is defined as the magnitude of the maximum displacement from the equilibrium position. So in this situation, we are known that the boat moves 6 centimeters above and 6 centimeters below. So the maximum displacement, so the magnitude of the maximum displacement is how much? 6. Yeah. So the
2.
yeah 6. Yeah, it's just 6 cm centimeter. We should know that if this is equilibrium, this is free, and this is the body. This is the equilibrium position. The body can move to right by amplitude A because the maximum displacement is A, and they also can move to the left hand, and then the maximum displacement is A. So the displacement is referred to the equilibrium position. So the distance, the total range is double A, but the amplitude is A. So this is the reason in this situation. So this is a bottle. The bottom is on the bottom. So the bottle can move up 6 cm, and it can move down 6 cm. So the amplitude is 6 cm, and the unit of the amplitude it is meter. So we should convert the cm to m. The second one, the period. We are on that. The bottle makes 1 complete up and down cycles every 5 seconds. So the period is 5 seconds. This one, the frequency. We already know the time. We already know the period, so we can find the frequency. The F is equal to 1/T, and the angular frequency is equal to 2 pi f. So the amplitude A is equal to 0.06 meter, and the period is 5 seconds, and the frequency F is equal to 1/T, and it's 1/5 5 seconds like this. So it's 0.2 hertz. And the angular frequency omega is equal to 2 pi f. So it is equal to 2 pi. The f is this. Now we look at a spatial oscillation. There are many kinds of oscillation. So we back to this. This is 2 kinds of oscillation. There are 3 kinds of oscillation. This one, and this one. So there are many oscillation. Now we look at spatial oscillation. It is the same harmonic motion. We use this as the same harmonic motion. So we are if a body wants to do the oscillation, there must be a restraining force. The restraining force is the key factor in the oscillation. So now we look at we can classify the oscillation according to the restraining force. Now we look at the simple harmonic motion. So the simple harmonic motion, it is a spatial oscillation. It is the force. The direct force or the restraining force can be described by the Hooke's law. So this is special, and this is also very common. So when the restraining force is directly proportional to the displacement from the equilibrium position, then the oscillation is called same harmonic motion. So we define the same harmonic motion according to the form of the restraining force. Because if the restraining force is directly proportional to the displacement from the equilibrium position, then we can say the oscillation is same harmonic motion, and then we can write it as SHM. The first letter SHM. So the restraining force Fx is equal to minus Kx, because the force is directly proportional to the displacement. So it is equal to Kx. The x is the displacement, and the K is a constant or is the coefficient. The minus means the direction.